Hey guys, we're going to jump into the second part of our info for intermolecular forces. So we do want to remember a little bit of review from last time. So we'll start with ions and ionic compounds. If you'll recall, ions require a full transfer of electrons, and so they are not bonded together by shared electrons. They are bonded together through electromagnetic attraction to each other. And so if we have something like calcium chloride with formula CaCl2, making this a +2 and each chlorine a -1, we have a ratio of 2 chlorines for every 1 calcium. What we introduced last time was we needed to go beyond just picturing an ionic compound as discrete particles, but more as just a bunch of positively and negatively charged ions all attracted to each other. Okay? Now, that is different from our covalent compounds in that with our covalent compounds, we do have these discrete particles where the different atoms are attracted to each other or bonded together through shared electrons. And so a methane molecule is actually a discrete molecule. It's not a methane molecule attached to a bunch of other or attracted to a bunch of other methanes. It's one carbon with 4 hydrogens. And then we also have, so these are our non-polars, and then with our polar compounds, right, we do still have discrete particles with those covalent bonds, but there is also some attraction between those particles. So we kind of have this continuum of ionic compounds, which are just essentially a bunch of charged particles at certain ratios, like we just showed with 2 chlorines for every 1 calcium, to polar covalent compounds, which are bonded covalently and discrete particles, but they are still attracted, those individual particles are attracted to other like particles, all the way over to our completely nonpolar compounds, which have very little, if any, attraction to anything besides what's inside that molecule. Right? So we have intramolecular, which is the bonds, that's this part, and we have the intermolecular forces, which is the attraction between the molecules, not the attraction between created by the bonds within the molecule. Okay, now that's all review. So intermolecular forces, right? Ionic compounds have very high attraction between the particles. Polar covalent compounds have a moderate degree of attraction. And we could describe nonpolar covalent compounds as having low attraction. Now, again, I want to remind you one more time, we're not talking about the bonds. Right, so if we have methane again, H, 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 I'm not talking about the strength of that attraction. Right? That is a intramolecular force, and that might actually be a fairly strong bond. I'm talking about if there were another methane nearby. Right? Would this methane have some sort of attraction to that methane? Since it's nonpolar, there would be very little, if any, attraction from this guy to this guy. Not talking about the attraction that occurs because of that bond. All right, I hope I've made that clear at this point. Now, moving forward. Intermolecular forces and solubility, right? We talked a little bit yesterday or last time about boiling point, right? So our ionic compounds have very high boiling points because those particles are very, very tightly held together. It's hard to separate those to turn them into a gas. Polar covalent compounds have moderate boiling points because they're not as held tightly together as ionic compounds. But there is still some attraction, and our covalent compounds tend to have lower boiling points. So referring to solubility, some rules I want us to remember is like dissolves like. And I'll talk about what that means here shortly. Water, we have to remember, is a polar molecule. And polarity, so if we have a polar molecule like water, it allows it to dissolve other polar and ionic compounds. So again, with water, if we look at the picture here, we have our oxygen part and our hydrogen parts, right? The oxygen part is negative, the hydrogen part is positive. we take something like sodium chloride, which is an ionic compound, what we have to remember is that's a bunch of sodiums attracted to a bunch of chlorines. The water molecules are able to actually pull those apart in solution because water has these charges attached to it. So it's essentially able to kind of separate those ions from each other. Now, contrast that with something like ethanol, right? So we have, again, water is able to dissolve ionic compounds. Water is able to dissolve polar molecules because like dissolves like. Water has charges associated with it, positive and negative. Ionic compounds have charges. Polar compounds have charges associated. Those charges are just a little bit weaker. All right? So water can dissolve ionic compounds. We could take something like ethanol, which is a polar covalent compound, and we have something very similar to what water has. We have a large enough difference in electronegativity that oxygen pulls those electrons a little bit closer to itself, and it's not shown in this picture, we also have those lone pairs. So this is asymmetrical, meaning it is a polar compound or a polar molecule. All right. Now, because we have some negative charge associated with this molecule, water is then, so again, if we picture our oxygen side being the negative and the hydrogens being positive, water is then able to take and get sort of in between the ethanol molecules. So if we could picture a whole bunch of these ethanol molecules around each other, so we have an ethanol with a plus side and a minus side, it's going to be attracted to another ethanol molecule, minus to plus, like this. Those charges, that plus side and that more minus side, are going to be attracted to each other. So there is some attraction through that polarity. Water, being highly polar, is able to sort of get in between and separate those. So we might have an ethanol with its minus and plus side, right? And we're going to have our water molecule attached minus to plus, and then plus to oxygen, minus like that. Those water molecules sort of get in between those ethanol molecules and are able to dissolve it. So again, water is able to dissolve ionic compounds and polar covalent compounds because of those attractions between what we call those dipoles, right? That positive side and that negative side. Now, if we take something like paraffin or oil, for example, vegetable oil, water is not able to dissolve those very well because things like paraffin, right, has no polarity. It's non-polar. Right? And those molecules are really big, so water has a hard time dissolving things that have little polarity or if the molecules are particularly large. Okay? So, solubility can be predicted based on the polarity of the molecule. If the molecule is nonpolar in a large molecule, water has a very difficult time dissolving it. If it is a highly polar molecule or an ionic compound, water does tend to do a very good job. Okay. Now, you might be wondering why this matters, but we'll get to that in just a second. Just remember what types of things water can dissolve, and you need to be able to sort of describe why. Now, moving on to aroma here in a second, but here's what we want to remember. Ionic compounds, we have a high attraction between particles, right? They have high boiling points and tend to be soluble in water. Polar covalent compounds, we have a moderate attraction, moderate boiling points, and also soluble in water. Non-polar covalent compounds, we have low attraction, lower boiling points, Whoops, excuse me. Right? And they're not soluble in water. So, getting to aroma. First of all, we had to understand those first two properties first, because things that have an aroma, they have two things in common. One is they are able to form a gas at room temperature. And two, they are soluble in water. Right? So one of the things I want us to think about first here is what types of things have lower boiling points. So that basically rules out ionic compounds. All right, so if it's going to form a gas at a room temperature, that means the forces holding those particles together, right, or preventing them from becoming gases, can't be all that strong. So compounds that tend to have an aroma, right, tend to not be ionic compounds because they don't form a gas. Two, they need to be soluble in water, which sort of rules out our nonpolar compounds. So what are we left with? Aromatic compounds tend to be polar covalent, right? Because they need to be able to actually form a gas at room temperature to reasonably well, and they need to be soluble in water. Ionic compounds boil at very high temperatures, typically, therefore do not form gases at room temperature. That rules those out. Nonpolar compounds are not soluble in water. That rules those out. So the types of compounds that we tend to be able to have a detectable aroma are polar covalent compounds. Now, why is that exactly? Well, first of all, the obvious part is in order for, let's say we have a liquid, right, for us to be able to detect that smell, it needs to form enough of a gas or vaporize easily enough that it can waft into our nasal cavity, right? So we need free particles in order to do that. Those would be gases. Right? So that's the obvious part. Now, why exactly does it need to be soluble in water for us to have a detectable aroma? So what happens, all right, so when we take a certain gas in through our nasal cavity, we have receptors, those are called olfactory receptors in an olfactory bulb that can then send signals to our brain to interpret. Right? But these are covered, essentially, we can think of as a barrier of mucus. Now, mucus is mostly water. So if we have a mucus layer, our nonpolar compounds are not able to pass through that mucus barrier because there's no way for that gas molecule to move through the mucus because it's not soluble. Our polar covalent molecules, though, can pass through that mucus barrier to the olfactory receptors, and then we can then detect an aroma. Okay? So, moving forward, things like hydrogen sulfide and ammonia, right? Both of them are gases at room temperature, right? They are both polar, right? And therefore, they both have very distinct aromas. Hydrogen sulfide has that rotten egg smell. And ammonia, if you guys have never smelled that, it's a cleaning solution, but it has, well, I guess you'd call it the ammonia smell. It's the only thing that smells like it. All right? Both very distinct aromas. They're both gases at room temperature, and they are both polar. So, going back to our essential question, you guys ought to be able to provide some sort of answer to this. Why do gas companies add hydrogen sulfide to natural gas? In other words, why are we able to detect hydrogen sulfide but not methane? Right? Hydrogen sulfide is a gas. Methane, also a gas. Right, so they both pass that. Are they able to form a gas at room temperature test? Why can we smell hydrogen sulfide but not methane?